So nuclear magnetic resonance is our third type of spectroscopy slash spectrometry that we'll be looking at. And it's probably the most powerful of all, and also probably a little more difficult too. So there's a whole chapter on it. I have this website posted on Canvas. All right, so NMR is usually what we call it, nuclear magnetic resonance, NMR spectroscopy. Like I said, it's probably the most valuable spectroscopic technique available, and it doesn't replace, but rather complements infrared and mass spectrometry. So just to review a little bit, what was mass spectrometry? Helped us find the molecular size and formula, so the molecular weight, and also some fractions or fragmentation. And then infrared spectroscopy helps identify functional groups. And then NMR spectroscopy is what we're going to learn now, is helps you get a carbon-hydrogen framework. And you'll see a lot more as we go along how we do that. Just one little note. Notice that it's mass spectrometry, but it's infrared and NMR spectroscopy. The difference is the spectroscopy is where you're actually measuring light. So some kind of like obviously infrared uses infrared light. NMR, as we'll see, kind of uses magnetic radiation. So they're all using some kind of radiation, whereas mass spectrometry is not really using light, it's just using electrons to kick another electron out. And so that's why it's not really called spectroscopy, but spectrometry. But you can just use spec. You can say infrared spec or mass spec or NMR spec or just NMR anyway, if you get them confused. All right, so NMR spectroscopy gives the number of each distinct type of atom of the kind being studied. There's a number of different NMR, but we are going to focus mostly on hydrogen, but also at the end we'll look a little bit at carbon. Obviously with organic compounds, those are the two most common elements. So one thing to keep in mind is that remember in mass spec and infrared, we don't look at every single peak. So we look at the most important ones, the tallest ones in mass spec, or the biggest absorptions in IR. In this case, you actually absolutely have to look at the entire spectrum. You have to look at each peak. If you ignore one, you're probably going to make a mistake. So and what's interesting, if you were actually worried about it and working in a lab, is that unlike mass spectrometry or NMR is non-destructive. So organic chemists who are doing research, making small samples of something, and they don't want to lose it, they want to keep it, it's non-destructive. So they're able to keep the sample afterwards. All right, so an important thing about NMR comes from the fact that many atomic nuclei spin. They act like they're spinning on an axis, and you can see it spinning right there. So because nuclei are positively charged, they can act like little magnets, so they spin. And interestingly enough, not all nuclei act this way, but only those with odd mass numbers will do that. And so hydrogen obviously has an odd mass number because it's 1. Carbon-12 does not, but there is an isotope carbon-13, so carbon-13 nuclei also has a spin. So Oxygen does not, nitrogen does not. So, so carbon and hydrogen, hydrogen being the main one that we're going to look at. So these magnets are random. And they're kind of in free space, and so some they're just randomly. But if you put them in a magnetic field, so you have a magnetic field, and you line these nuclei up, what happens is the spinning nuclei will line up with the magnetic field. And when they do, there's only two orientations that are allowed. So there's the alpha spin, which is let's get a marker here. So there's the alpha spin over here, which sometimes is called the positive 1/2 spin. And then there's the beta, which is negative. And notice that here's the magnetic field. And so what's happening is these are creating their own little magnets, because when a charged particle spins, it creates a magnet. And so that's why they line up with the magnetic field. And so they either will go spinning, I guess this one's counterclockwise and this one's clockwise, but it's not important. One will be the plus 1/2 or alpha spin, and one's the minus 1/2 or beta spin. It turns out that the alpha nuclei are actually slightly lower energy because they are lined up with the magnetic field, and then the other one, the beta, is lined up against the magnetic field. But they're not going to be random all over the place. They're both going to be up or down, either with the magnetic field or against the magnetic field. All right, so then what happens is these nuclei that are lined up with the magnetic field are irradiated with electromagnetic radiation of different frequencies. So, but it'll be the proper frequency, so it'll be the one that particularly does something called a spin flip. And so it's the frequency that allows the spin flip. What's a spin flip? The spin flip is when alpha goes to beta or beta goes to alpha. So it literally flips up or down. So the alpha will spin flip up to the higher energy state. The beta will spin flip down to the alpha. So when the spin flip occurs, the magnetic nuclei then are said to be in resonance with the applied field, and so that's where the name comes from, nuclear magnetic resonance. It's a little bit similar to if you go to the hospital. So MRI, magnetic resonance imaging, is related to this. I don't know very much about MRIs, but it's going to be somewhat related to this magnetic resonance and electrons in resonance with the magnetic field. All right, so this is not a super important slide, but the energy difference between the two spins, it depends on a couple of things. It depends on the identity of the nuclei. So, if it's these are all hydrogens or protons, so hydrogens. If it's a carbon, it will have a higher energy difference. But it also depends on the magnetic field. So what you see here is this is an increasing magnetic field. So if you increase the magnetic field, you're going to also increase the energy between the two spins. And so a higher frequency of radiation is required for a spin flip. It'll kind of become important in a little while when we talk about splitting. But so the higher the magnetic field, the more energy, the more radiation, the higher the frequency that is needed for a spin flip. All right, so here's what happens. Is a sample is dissolved in a solvent that doesn't have any hydrogens in it. And it's placed in a tube. You can't have any hydrogens in the solvent because obviously we're trying to find out about the hydrogens in the sample. Then you can see that it's put down inside a magnet. Here's the magnet. It's a spinning, the tube spins to create, to help it keep it kind of even. So when it spins, and it's in the magnetic field. And then it is radio, this is the radio frequency transmitter that will scan sort of through the sample, and then you receive the results on the other end. So here's the magnet, so it's down in the magnet, and then this is the radio waves that it is irradiated with. That's a great word. What they'll do is scan different radio wave frequencies, and so the field, when the nuclei reaches resonance, it will be a particular, it'll absorb energy, and so that will be noted by the detector. The spin will flip, the energy loss is measured, so the frequency that's being put in will be absorbed, and then it'll be noticed that it's decreased, and so it'll be measured. And so you can use different frequency, different carbons will or different hydrogens will absorb at different frequencies, and we'll talk about that in a minute. Okay, so the NMR scale is usually, it's called the parts per million scale, ppm, or sometimes you'll see this little delta. This is the lowercase delta. So you'll see either ppm or delta on the x-axis. And then, and this is not super important, but what it is the ratio of the shift in hertz divided by the total frequency of the instrument. So in that way, that you can compare different instruments if they have different magnetic fields. Since you divide by it, you kind of even it out, and so whatever instrument you use, you should have the same frequency or your same parts per million for whatever compound you're scanning, and it doesn't matter what instrument you're using. So that's why they do that. Sometimes a little bit of this compound, which is called tetramethylsilane, or TMS, is used as a calibration because we kind of make this compound, which has 12 equal hydrogen, it will be the mark for 0. And so that's often put in there just so that you can compare it to everything else, compare everything else to it actually. So here's what an NMR spectrum looks like. Here, as you can see, is the molecule that we're looking at. And you can see here that this is the TMS, so that sort of indicates the 0 marker. You can see here it's ppm on the x-axis. It usually will start, and it goes, you read it to the left, so it starts at 0 and it gets higher ppm. And we'll talk more about how you know this, but for right now, we can see that there's 3 hydrogen over here. Since this is a hydrogen, it's only detecting the hydrogen. So the 3 hydrogen over here are this peak, or give rise to this peak. There's 2 hydrogen right here, and they give rise to this peak here. And then they're just showing you 1, but remember there's 5 hydrogen here. Can't draw. 5 hydrogen that are equivalent to each other here, and they give rise to this peak. And so you can see that different types of hydrogen, depending on where they are in the molecule, will show up at different locations. So similar to what we've already been doing, and we'll be able to identify where they're located along this axis will help us determine what kind of hydrogen we have in the molecule. All right, so let's go a little bit more carefully at a molecule. So here's an NMR for this molecule, which is toluene. You don't need to know that, but that's what it is. Notice here that when you run the spectrum, you only have 2 peaks. One here at a little bit above 2, and one here at about 7. And so even though we only see 2 peaks, they represent 10 hydrogen. So this is C8H, C10. So there's 10 hydrogen represented by these 2 peaks. But what's important to note is that there are only 2 kinds of hydrogen. So what you want to do is sort of look at their neighborhood, or how compare them to other hydrogen, and sometimes they act the same. So it turns out that you can see from symmetry that these 3 over here and these 3 over here are actually identical to each other. So they all end up flipping, doing their spin flip at the same point. So they actually are all here under this peak right here. And I'll talk about how you know which one is which in a little while. And then you can see that there's 4 hydrogen directly attached to the benzene ring right here, and those 4 are also identical to each other. They're all 4 attached to the benzene ring, and because of symmetry, they're all alike. And so these are this peak. These 4 hydrogen give rise to this peak, and this 6 hydrogen give rise to this peak. So all nuclei that are identical in the molecule will show up as one peak. You might note this video of NMR spectroscopy. We saw very similar ones in IR and mass spec, and I have posted this video also in Canvas. All right, so how can you tell if 2 hydrogen are equivalent or not equivalent? So in other words, will they give rise to the same peak or not? So, and here's why you need to know. All protons are all hydrogen, remember, protons that are chemically, if they're in the same identical environment, then they will give rise to the same peak, or they will have the same chemical shift, or in other words, they'll need the same amount of energy to flip their spin. And so notice that in all 3 of these cases, you're only going to get one signal because all the hydrogens are equivalent. So you see here that there's 10 hydrogen, and they're all considered equivalent because of symmetry. There's 2 hydrogen on each carbon, and it's in a ring, and there's nothing else there. So this will give you one peak. This one will also give you one hydrogen peak because these 3 hydrogen and these 3 hydrogen are equivalent to each other. On a benzene ring, you have 6 hydrogen. All 6 of them are equivalent to each other, so you'll only get one peak. Now, how can you tell if you're looking at 2 different hydrogens? You want to know, are they identical, or are they going to give rise to the same compound, or the same peak or not? And so one thing you can do is compare the hydrogen, and what you can do is replace the hydrogen with an X, the 2 in question, and then compare the compounds to see if they're identical or if they're isomers to each other. So notice here, I want to know, are these hydrogen and are these hydrogen the same, or are they different? Well, what I'm going to do is I'm going to take one of these hydrogen and replace it with an X, so just something. And then I'm going to do the same thing over here with this hydrogen, and I replaced it with an X. So now the question is, are these 2 compounds identical, or are they isomers of each other? And hopefully you can see that they're identical, because whether you start counting from the left to the right or the right to the left, like let's say that was a chloro, it'd be 1 chlorobutane either way. So it's the same compound. So these 6 hydrogen, in fact, will give rise to the same peak. In the same way, we could look at these 2 hydrogen, these 2 pairs. These will also give rise to one peak. So this molecule should give you 2 peaks, because these is one kind of hydrogen and this is another kind of hydrogen. Anyway, going back to the original ones, if you have 2 identical hydrogen, or in this case 6, they are considered homotopic. homotopic. And they give, if you substitute them, they give rise to identical compounds. So now, what if I'm trying to compare these two? And we kind of already saw from the last slide that they're different, but how will you know? Okay, so let's replace this one with an X and we get this compound. Let's instead replace this hydrogen with an X, and notice that these two are not identical compounds anymore. They're constitutional isomers. And so that means that the two hydrogens in question will not give rise to the same peak. They're not identical. There's a little bit of when we I know you don't want to hear this, but when we have chiral molecules, sometimes there's a little bit of confusion there. So what if we have enantiomers? It turns out, so there's more subtle possibilities. They look like they're identical, but in fact, if they're replaced, they might look like enantiomers. So that's what they're saying too. Are these hydrogen the same? Notice they're on the same carbon. Are they the same or are they different? Well, generally speaking, if this is the case, and notice that, like, let's replace this one with the X, or let's replace this one with an X. Notice that now this is a chiral center because you have 4 different attachments, and they are enantiomers of each other. Well, it turns, so these two hydrogen are said to be enantiotopic hydrogens from each other. And even though they're not actually identical, they're still electronically equivalent, and so they will give rise to the same peak. So you almost always, and we'll see an example that where this is not true, oftentimes in a ring, but usually if there's 2 hydrogen on the same carbon, we can assume that they give rise to the same peak, although that's not always true, but usually it's true. And so here's the 4th possibility. What if we start with a molecule that's already chiral? So here we have a chiral center right here. And now we're going to see how do these 2 hydrogen relate to each other. Well, if I replace this hydrogen with an X or this hydrogen with an X, we actually end up with diastereomers because this chiral center over here hasn't changed at all, but these carbons are mirror images of each other, but this center has stayed the same, so that's why they're diastereomers. So these hydrogens are actually called diastereotopic hydrogens, and they are neither chemically nor electronically equivalent, so they actually would give rise to 2 peaks. So this is one of those times when it can be a little confusing. Now here's the thing, is they'll have 2 different peaks, but they're actually going to be pretty similar to each other, so sometimes they blend and you might only see 1 peak. But I don't want you to worry too much about this, especially not for now, maybe when we get into the lab and look at some examples. But so technically there's 4, but really the first 2 are the 2 that you should focus on. You know, notice if they give rise to identical compounds or to stereoisomers. Isomers, not stereo, I'm sorry, constitutional isomers. All right, and here's one more possibility, and this is where I said, you know, so you probably 3 and 4 you don't need to worry about so much, but this one, especially if a molecule is restricted. So here you see a double bond or a ring. This is what I was talking about a little bit earlier. If there is a restricted bond rotation, then often you'll see two hydrogen on the same carbon acting differently. So for example, here on this one on the left, since this bromine is here and it's cis to this HB, and HA and HC are cis to each other, then what you can sort of see, because they can't rotate at all, that HC and HB are going to be different. Obviously HA is its own hydrogen, but then these two being different, the one closer to the bromine will be a little bit different than the one that's further away from the bromine. Similar on a benzene ring, you've got the bromine here, and you can see that the HAs are the closest to the bromine, and then the Bs are a little bit farther away, and then the C is over here. So actually you're going to see they're going to be really close to each other, but you're going to see 3 different peaks in this case, and this one will also give you 3 peaks. And then the same thing over here on the right. Now these two are the same because they're in the same kind of position with bromine, but then you can see here that the HA and HB are going to be a little bit different depending on this is the HA is closer to the bromines than the HB. So this one should also give rise to 3.